This is Arish. My project is based on NLP, that is sentimental analysis on text dataset. The main aim of this project is to build a sentimental analysis model capable of classifying tweets as either positive or negative by using natural language processing techniques. The goal is to analyze textual data and identifying the sentiment expressed in the tweet, which can be valued for understanding public opinion on various topics. To start to start my project, I take one dataset from the Kaggle and I downloaded the dataset on my Google Colab by using this code, and then I unzip the dataset which I downloaded from the Kaggle. For performing this performing this experiment, we need to import some certain libraries and certain tools for this experiment. Like we have to import some torch, and we have to import optimizers, we have to import data loaders, we have to import dataset, we have to import test train test splits and classification reports and confusion matrix and certain libraries which are needed for this project. After downloading the dataset, we have to perform some pre-processing steps. For that, we have to the main important pre-processing steps in the project is to first we have to remove the unused columns in our dataset. for that for that in my dataset I have tweets id and label. First I remove all the IDs and tweets in my data frame, and I save the tweet as a text, and I saved it as a string. After that, I change the labels positive or negative as a numericals like 1 or 0. After that, I drop all the null values in my data set, and I drop all the duplicate values in my data set. Finally, I'm getting the clean data set by using some pre-processing steps like removing unused columns and null values and duplicate rows. After after performing the pre-processing steps, we are using the tokenize function, which converts all the text as to lower cases. After that, we are using this build vocabulary function. This function takes a list of text and counts how often each word appears. It then creates a dictionary called vocabulary, where each unique word assigns a number. This dictionary starts from index 2 for the first word, because bad and unique are the special tokens. Mainly this helps in converting the words into unique numbers, which is important for text pre-processing in the machine learning models. Finally, the vocabulary is saved in a file called vocabulary.json. After that, we have to convert the text to numerical values. We define a function called text pipeline. This converts text into numerical values. It takes a text and vocabs, and it splits the text into words using the tokenize function from the previous code. Then it looks up each word in the vocabulary and gets the corresponding number. If the word is not found in the vocabulary, it replaces with unknown, which stands for unknown words. The result is a list of number where each number represents a word in a text. and then we have to convert labels into numerical values. The code then converts the text labels positive or negative into numbers. It uses label map where positive become 1, negative becomes 0. The function map the function map is used to replace the text labels into the data frame which corresponding numbers 1 or 0 for negative. After that we are defining certain classes like text dataset in which we have a function called init. It accepts text labels and vocabs. It stores the inputs as a list like self.text, self.labels and self.vocabs for easy access later. And we define here length function which defines the length of the dataset, how many items are in the dataset. This method returns the number of texts in the dataset which allow PyTorch to know how many data points in the is available. And we define get function. This method is used to retrieve a specific data point, a text and its label from the dataset using an index IDX value. First it checks if the index is valid within the bounds of dataset. If it is not, it raises an index error. Finally, the text is processed to text pipeline, which converts text into numerical values based on vocabulary. Finally, it returns processed text as numbers along with label. After that, we defined another function called pad sequence. This function used to pad text sequences so they all have same length. This is important because machine learning models often requires input to be of uniform size. Finally, this function returns two things: a tensor of padded text and tensor of labels. The result from this is ready to feed into machine learning model. After that, we define certain functions like train test split or train test split because it is used to split the data into various types like test text, train labels and test labels, etc. After that we are using the text data set text data set. Mm, These data sets are used to manage the text data and labels, and they are for necessary and they are for loading data efficiently. After that, we are using the data loader class. It is used to load the datasets in batches, which is efficient for training the machine learning models. Each loader is responsible for loading the data of respective datasets like train dataset, validation dataset, and test dataset. Finally, we define the model text classification model. This class defines a neural network model for text classification using LSTM. The purpose of this model is to take input text and predict its sentiment, that is positive or negative. For example, the main components of the model. First, this int method. This is where the each layers of the models are defined. We have self.embedding. This is an embedding layer that converts each word into unique number or dense vector. We have self.lstm. This is an LSTM layer or of type of recurrent neural network that can process the sequences while remembering information over time. We have embedded dimension. This is the input size which is represented by an embedding. We have addend dimension. We have self.fc. This is a fully connected layer that maps the output of the LSTM to output dimension. In binary classification, positive or negative sentiment, this typically have an output size of 1. We define self.sigmoid. This is a sigmoid activation function that converts the output of the fully connected layer in between 0 and value, making it suitable for binary classification. Finally, we define forward method where the input flows through the model. Embedding. The input X, which is sequence of number representing words, that is embedding layer converted into dense vectors. And we have LSTM. The embedded text is passed to LSTM. The LSTM process sequence of old embeddings, and the output includes hidden layer, which means the output from the LSTM, that is hidden state, is passed to the feed forward system, is passed to the fully connected layer through sigmoid function, which outputs a value between 0 and 1 representing the predicted probability of certain class. In simple terms, in simple terms, to explain the model, first it turns each word into text, each word of a text into vector that captures its embedding. Then the process the sequence of word vectors and remembers the information in LSTM. Process LSTM we use the final hidden state of the LSTM to make the prediction and convert the prediction into a probability using the sigmoid function. After defining the model, we have to initialize the model by using some certain hyperparameters like vocabulary size, embedding dimension, hidden dimension, output dimension, learning rate, and number of epochs. After initializing the model, we have to pass the text and tweets into the model. First we have to convert the text into embedding layers. After converting the words into embedding layer, we have to pass to the LSTM. After passing to the LSTM, we will get the hidden dimension from the LSTM. We pass the hidden dimension to the feed forward system. We got the result. In simple terms, we are using training loop. The model learns by adjusting its parameters over multiple iterations how well its prediction matches the true labels. After each epoch, the model is tested on unseen validation data to check its performance. And after running this model, through the training dataset or validation dataset, we have to find the best model. For finding the best model, we are using the one condition like if the validation accuracy is greater than the best accuracy, then we will stop the validation, and we will save the we will save we will save the model by using the function called model. By the way, we save the model by the function called best state model. In simple terms, the model is trained in multiple epochs, where in each epoch it learns from the training data, makes predictions, and updates its internal parameters like weights, biases, and some parameters in LSTM. After every epoch, the model is validated to check how well it is performed on unseen data. The model performance is tracked using loss functions. How far our prediction is from the true label and accuracies. After that, the best performing model is fine based on the validation accuracy is saved for the future use. After that, we plot the training and validation accuracies. The main purpose is to visualize how the loss changes over the epochs for both training and validation dataset. If we observe this plot, we have two lines. One is blue line, one is orange line. This blue line represents training loss. This orange line represents the validation loss. In the x-axis we represent epochs, and y-axis we represent laws. Similarly, we plot the accuracies. We plot Similarly, we plot the accuracies over epochs for both training and validation dataset. If we observe, we plot the epochs on x-axis, we take the accuracies on y-axis, and again we have two graphs. One graph represents training accuracy and another graph represents validation accuracy. After that, we are performing evaluation and test data. The main purpose is the after the training the model is evaluated on test data which was not seen during training or validation. This gives us an unbiased performance measurement of the model. This evaluate evaluate how well the model is performing on data it has never seen before. Finally, we perform classification report. The classification report gives a detailed performance evaluation of the model, providing different matrices like precision, recall, F1 score, and support for each class. Here we represent the classification report which contain precision, recall, F1 score, and support score. This report helps access the performance of the model in terms of various matrices, precision, recall, F1 score, which are crucial for evaluating how well the model is classifying the text data. After that, we created a confusion matrix. The main purpose of the confusion matrix is a performance measurement for classification problems. It compares the predicted labels to true labels. It compares and showing how well the model is performing. It helps us to understand which classes were correctly predicted and which are misclassified. Finally, we plot the ROC curve. The main purpose of this ROC curve is it is a graphical representation that helps to evaluate the performance of a binary classification model, where the x-axis represent the false positive ratio rate and y-axis represent true positive rate. As you move along the graph, the threshold, the decision boundary for classification is varied. Mainly, the ROC curve is particularly useful for you to evaluate the performance of our model. It helps us to understand how the model balances the false positives and true positives, and it gives a clear view how well the model can be discriminate between two classes. This AUC score gives a simple aggregate measure of performance, especially when you have an imbalanced data set. Now we are finally deep dive into our conclusions. First, this table. First, if you observe these ones, you observe this one precision, recall, and F1 score. These represent these numerical assess. These are the numerical assessment results for the classification model through precision and recall performance as well as F1 score and accuracy measurements for negative and positive classes. The predictions for negative instead by the model demonstrate 90% accuracy, with significance that only 10% of negative predictions are incorrect. The model recalls 92% of the actual negative cases with, with, with precision accuracy of 90%. A high F1 score value of 0.91 indicates excellent precision recall performance, and the class-wise accuracy reaches 87%. 87 87%. The model delivers a lower F1 score of 0.72 because it achieves a 0.75 precision and 0.69 recall for the positive class. The positive class demonstrate an accuracy rate of 84%. Accuracy of 84% because it contains higher number of positive errors. And if you observe this graph, This figure represent the learning process of the model through multiple epochs, displaying the training and validation accuracies. The model classification accuracy assessment happens through this confusion matrix that matches the predictor labels to actual labels. The predictor class label appears on y-axis and true label class represent on y-axis. A confusion matrix contains four distinct classification. This is true, negative, false, positive, false, negative, as well as true, positive. The true negative value stands at 1090, representing the number of correct negative instance predictions for the model. The false positive FV, which reaches 92 while indicating the 92 negative examples appears as a positive examples. The model misclassified 124 instances of positive samples as negative cases, which corresponding to false negative value. The model correctly identifies 278 positive instances according to true positive. The model efficiently detects the negative cases instantly according to the confusion matrix. And this figure displays the ROC curve. It is to evaluate how the model performs at different thresholds. The FPR values appear on x-axis and TPR values appears on y-axis. The orange line plot shows the how model classify inputs as it changes the threshold value. The diagonal dashed line stands as a baseline for random classifier. A 0.92 AUC value significance excellent performance capabilities of the model. The model demonstrates effective distinction between positive and negative classes when AUC curve is evaluated. The sharp beginning section of the curve indicates the model produces high true positives together with minimum false results. Such application requires a robust system capability of accurate class distinction because of this model proves it is self to be suitable. Finally, conclusions. The field of sentimental analysis advanced remarkable during recent years because of improved NLP and machine learning capabilities. Analysis of sentimental and continues to show rising significance relevance across several domains which covers business sectors through politics and medical industries as well as social media platforms. Finally, we are coming into the our deployment part where we are going to evaluate the performance of this model by using some tweets to analyze it as whether it is showing positive or negative. For that, I am creating the deployment for this project by using AWS and AWS by using AWS. Here, here this is the our deployment. In this, if you it is used to identify the text as a positive or negative. First, if you try with anything like for analyzing the tweet and typing like some sentences like I'm feeling sad on stomach. Let's analyze this tweet. It is showing negative. And if you are using I'm happy today, it shows positive. And I'm lazy, it is also showing positive. Sometimes it happens like I'm tired, it is also showing positive. This is how we are this is how we are doing the sentiment analysis on web app. Finally, thank you.